Well, it's 9 o'clock, so good morning. We're going to get underway with the lecture. Can someone, I'm just watching Discord at the moment on the questions lectures channel. Can someone just give me a thumbs up that the audio is all coming through okay on YouTube? Wonderful. Thanks, Paul. Thanks, Ranch. That's great. Wonderful. So welcome to week 2, Monday of week 2. Big week for the whole class last week. We kicked off a class of almost 800 students. Lots of work behind the scenes to get things underway, and also lots of things for you as incoming students to get your heads around. Couple of points before we get underway with today's lecture. One is there's quite a lot of traffic on Discord at the moment about registering as a student. As I said, we have just under 800 students in the class at the moment, which is great. About 500 of you have registered as a student within Discord. What that means is that 500 of you have run the admin bot to register your name within our system. That means you get access to most of the interesting and relevant content for this course. What that bot does, it reconciles the information that you tell us and matches up the nickname you have in Discord with your student name and number in our student registration system. So the only students we let into the student role are students that we know are enrolled students. So that's great. 500 of you have done it, several hundred of you yet to do it. And I'd strongly encourage you to do it because, as I say, you're starting to miss out on key information there. There's information in announcements in general about how you do that registration, and I'd strongly encourage you to do it as a matter of urgency as we go forwards. Wonderful. The second thing I wanted to say before we get started was just a quick recap on what I expected you to have done last week. We saw an introduction to the Python language, but in particular, we saw the PyCharm integrated development environment, the IDE. Going forwards, I'm just going to use the acronym IDE, or PyCharm IDE. The expectation is that either through the face-to-face labs or the Zoom labs, or both, that you've now had a chance to use the console in PyCharm and also write your first small programs or scripts, only 2 or 3 lines long, just to get you started. That's the expectation that I've got going into today, because what we do from today is we really start taking that to the next level, and we're really starting to move from today's lecture forwards into getting Python to do useful stuff for us. So here's an overview of today's lecture. The slides here I posted on Discord last night. They're also in the Blackboard Week 2 course materials. So there are 4 things I want to work with you through this morning, and they're listed here in the lecture overview on the screen. In order, we're going to see our first Python program that uses something called a library function. We're going to import, I'm going to then generalize that in the second chunk of today's lecture and show you how to import from code from other places, from things called modules and sometimes packages. We're then going to introduce just the rudiments of plotting, so being able to produce a plot on the screen of data that you've calculated in Python. And finally, we're going to look in a little bit more detail at plotting and printing. So the way I've structured today's lecture, bit of an experiment. I want to get some feedback from you on Discord later on how it works. But we've structured it in these 4 chunks, but in each chunk, the pattern's going to be, I'm going to give you some principles in the lecture, and then we're going to switch to a live demo in which I'm going to illustrate those principles using PyCharm. And then we'll do the same thing for each of the four sections that you see there indicated in the lecture overview. In red, and the numbers on the far right-hand side of each of the 4 dot points there, you'll see are the section numbers in the text. And the lecture content that we present today follows the text in this case, it follows the text quite closely. That doesn't mean that we'll be looking at all the content with equal coverage. Some content we'll skip over in the textbook fairly quickly. Other content we'll really pause and understand what's being covered. In this week and in all future weeks, what you'll find is a pretty tight integration of the lecture content that's presented in that week and the labs, both the face-to-face and the Zoom labs. So Brenton posted last night on Discord the lab sheet for week 2, and we've worked pretty carefully behind the scenes to make sure that the coverage between the lectures and the labs dovetails together. So in some cases, there'll be a repetition of material you've seen in the lectures while you go about your lab activity this week. In other cases, you'll find that there's some concepts that are drilled down to in more detail in the labs and only touched on briefly in lectures. And we do that for a reason. Sometimes, and some of the content in today's lecture this is true. What you find is that the principles are fairly straightforward, but you really get the learning by doing it at PyCharm, either the console or writing a program. So something that could be gone over in a couple of minutes in a lecture might take you half an hour to get your head around at PyCharm, or vice versa. So that's the lecture overview of today. Let's get going. We're going to solve a problem. You could call it an engineering problem. It's our first real calculation problem that's going to introduce some mathematics. And so the scenario you have here, coming straight from the textbook, is we've got a ball, in this case a soccer ball, and it's located 10 meters away from us and 10 meters in the air. And the question that we need to solve is to calculate the angle theta here, indicated between the angle between the horizontal and a line of sight to the soccer ball 10 meters in the air. Now we already know the answer to that question because of the particular geometry here. The ball's 10 meters away from us and it's also 10 meters in the air. So we know the answer. The answer is 45 degrees. So you might ask the question, why bother calculating it if we already know the answer? And the reason is that we're going to use that particular case, 10 meters, as a test case for a computer program that we write because we know the answer in a particular case. So we're already looking ahead past the actual solution of the problem to how we might verify that our solution is correct. We want our program to be more general than just 10 meters. So we want to calculate it for arbitrary X and Y, but we're going to use the 10 meters and 10 meters as a test case. Now, by high school trigonometry, the tan of the angle theta is equal to the height Y over the distance X. You might remember it from school as being the tangent of an angle in a triangle, a right angle triangle such as this, is the opposite distance divided by the adjacent distance. In this case, Y, the opposite edge to the angle, and the X edge, which is the adjacent. So trigonometry tells us that the tangent of that angle is Y on X. But we don't want to know what the tangent of the angle is. We want to know what the angle is itself. So our algorithm is to back calculate from knowledge of the tangent what the angle itself is. And in order to do that, the algorithm that I've identified here on page 2 is we use the inverse tangent, or sometimes known as the arctangent of the ratio Y on X. And just as a review, if you're scratching your head back to your high school trigonometry, the tan inverse of Z, the arctan of Z, calculates the angle theta such that the tangent of that angle is equal to Z. So if we pass Z into the arctan function, we get the angle whose tangent is that argument. So there's our problem setting. We've got an algorithm and we've got a test case, namely we know the answer when we know that the distances are 10 meters and 10 meters respectively. Okay, So here is a 4-line Python program that calculates the angle and displays that angle, or at least sets out to. So what are the key features of this program? First, we define X and Y, our horizontal and vertical distances, respectively. We define them, and it's always a good idea to indicate with a comment in the Python source code, which is a reminder. X and Y are not particularly descriptive variable names. If I were writing this code, rather than following the code that's in the text, instead of X and Y, I'd probably use something like horizontal distance and vertical distance, and I'd come up with a variable name that reflected the intended meaning. There was a good question on Discord last week about do variable names have to be single characters, and my answer to that question is absolutely not. It's good programming style to choose variable names which reflect the quantities of interest. In this case, the horizontal and vertical distances. The third line of code that you see here, angle equals a tan y on x. That's going to do the calculations, and I'll say more about how that happens on the next slide. And then the final line of the program is to print the angle. Although you can see it's not a direct printing angle, there's something to do with pi and 180 there too. So let's unpack what the third and fourth lines of this program do. This expression that you see on the top of page 4, the angle equals a tan y on x, this is really important. This is our first use of a function that we've seen in Python. And the function that we're making use of is the inverse tangent function. In Python, that function is known not as tan to the -1, but a tan. That's the arctangent. So this is our first use of a function. A tan is a function, and you can see that even though we use this code here, this function call. So when we have a line of code that makes use of that function, we say that the function is called. We haven't said where that function comes from, and there's more to say about that in the slides to follow. In fact, that's a key point of this roughly the first half of today's lecture. The ratio of y on x that you can see that is passed into the function a tan, that y on x, or the quantity that's passed to that function, in general is known as the argument of the function. And then a tan does its thing, does an arctangent calculation, details of which don't matter, but the existence of that function does. And what it does is returns an angle, which we can then assign to the variable angle. Looks good. The final line of the code, which I've reproduced here on page 5, is we need to do a conversion. Remember I said that we know the answer. The answer when x and y are 10 meters respectively, the answer to the angle is 45 degrees. Degrees is the key point here. Python's a tan function, which remember returns an angle corresponding to the argument that's passed to it. Python's a tan function returns an angle in radians. So we need to do a conversion between radians to degrees. And if you think back to your high school mathematics, if you multiply a radian angle by 180 on pi, you convert it to degrees. So now we've got the 4 ingredients. We've got x and y defined. We have a function called to a tan in the third line, and then we print the answer in the fourth line. However, when we run that program in PyCharm, and I've got a little screenshot here of what happened when I run it, and I'm going to do this live with you when we've finished the principles part of this section. I've taken a screenshot here. You can see that the red text here says something about name error, name and a tan is not defined, and I've reproduced that error message for you there in the middle of the screen. As a general rule, and Python's no different, as a general rule, error messages in programming environments are generally a little bit confusing. The interpreter knows when it's got a problem with code. How it communicates that information back to the programmer, the user, is less than clear. But in this case, it's pretty clear. Name error, name A10 is not defined. And the problem is here that the Python language does not have the A10 function built in. So if you've got a pocket calculator, a desktop calculator, you might reasonably expect that a whole range of trigonometric functions are built into that calculator. You don't buy a calculator and then have to do anything else to get it to work. It does useful things, does calculations for you without having to be modified in any way. But Python, again, in keeping with many modern languages, doesn't have the A10 function built in. We've got to actually incorporate knowledge of that trigonometric function A10. And we do that using a process known as importing. So Python has some functionality built in. We've already seen a little bit of that functionality last week. It's got the ability to add, subtract, divide, and so on, and some logical operations, which we'll touch on from Thursday and beyond. It's got some functionality, but not much. Now that might seem fairly restrictive to have a computer programming language that doesn't have the functionality of some trigonometric functions. After all, this is a language we're using for engineering computations in this course. What's going on? Well, the solution is that if we don't have the functionality built into the language, we can import it. And it's quite straightforward, and I'll show you how to import the A10 function. But the point here is that to activate that functionality, we have to explicitly import it. We actually have to put a line in our code to say, I want to import the function A10. And in this case, the A10 function is grouped together with many other mathematical functions in what's called a library module called math. And so what I've done here you'll see in the red emphasized text, this is where I'm using terms that we've not previously seen. So every time you see red text like this, it generally means that we're introducing a new term. That means you're not expected to have seen it before. So the line of code that we need to introduce in our program is shown at the bottom of the screen here. We need a statement that says from math, import A10, pi. What that does, it tells the Python interpreter from something called the math library, we want to bring in from outside the function A10 and the constant pi, 3.14159, and so on. So not only does Python not know about trigonometric functions like A10, it doesn't even know about pi. If we want Python to know about it, we have to tell it to import. And we can't just say import it from somewhere. We've got to say where we import it from. And in this case, we import it from from what's known as the math library. And so our second attempt at the program is shown here on the screen. It's generally a good idea at the top of your code to use your import statements. And so now we've got a 5-line program, the same 4 lines as before, plus an additional line at the top that says from math, import A10 and pi. And if we run that script, and I'm going to do it for you live in a few minutes, it will correctly produce the number 45 as output. So it's given us the angle in degrees corresponding to the horizontal and vertical distances X and Y respectively. So this simple operation of importing external functionality is one of the real strengths of Python. Indeed all modern computer languages, and certainly the ones that are used for engineering computations, have the ability to bring in a capability that's been developed elsewhere. It's it's a hallmark of modern computer languages that an engineer to solve this problem doesn't have to worry about precisely how the A10 function works. They just need to be able to import that functionality from outside. But what an advantage of Python is, I won't say it's a unique advantage, but it's increasingly a unique advantage. It's a very powerful advantage of Python, is that there is so much code development going on that the external functionality that's being provided is literally impossible to keep up with. So things like trigonometric functions and constants like pi, they're pretty straightforward. They're well developed, but you might want to introduce code that works with large data sets, big data, for example, or you might want to bring in code that does something to do with object recognition in images, or you might want to bring in code that does machine learning. Python very well suited to all those applications. There's so much external code being generated that it's possible to import that code and have access to it, even though you didn't write the code, even though you don't care about how the code's implemented. As engineers, we're always bringing in external tools to help us solve our problems. This is the first example we've seen of it in Python. So we're importing from an external library some external functionality. There's another way of importing. It's a variation. I shouldn't say it's necessarily another way. It's a related way of importing. So the code here that you see on the screen looks quite similar to the previous code. Can you see the difference though? There's some small differences here. The import statement is different. Instead of it, the previous statement said from math import A10 pi. This import statement just says import math. So what that import statement says is that it tells the Python interpreter, I don't know what functions or constants I'm going to make use of yet, but I want you to set me up so that I've got the ability to make use of that math library if I need it. So that's the first line. The import statement sets you up, but it doesn't do anything beyond that. It just says to Python, I know I'm going to use the math library later. Just prepare me to do that. So that's the second way in which this code's modified from the previous version of this code is that you see the fourth and fifth lines, angle equals math.A10 and print angle on math.pi. The math.A10 and the math.pi are how we specify where the A10 function and the pi constant come from. It's like saying we're being explicit now about where we get A10 and pi from. The previous version of the code just says make these available and then use them as you wish. The second version of importing, the variation, has to use this math dot prefix. And it's the prefix so prefix is code that comes before. So it's math.a10 and math.pi. And so this second way of importing uses prefixes. Now, both the ways of importing, both the way that you see on slide page 8 and on page 9, both of them are in common use. But the preferred way is the second way with the prefix, and I'll explain why after we demonstrate this live demonstration of a Python program with a library function. So what I'm going to do now is just take a few minutes, and I'm going to run a couple of bits of code live with you here now on the screen. And I'm going to use a combination of, I'm going to use it just using some functions. So what I'm going to run for you first is, bear with me, presentation mode. I'm hopeful that you can see those 4 lines of code. These are the first example, the code that I gave in this morning's lecture. So the 4-line version, we define x and y, we calculate the angle as the arctangent of the ratio y on x, and then we print the angle to the screen. And if we run that code now, Here's the error. Remember I said the error? The error is that the ATAN function's not defined. That was the problem. So that was the first example where we ran it and we get the output that it says it's not defined. So the second version of that code is the version that you see on the screen there now, where the only difference between this version and the version that didn't run a minute ago is this line at the top that I've highlighted in blue. From math, import ATAN and pi. So this is telling Python, if you we're going to use the arctangent function and we're going to use the constant pi. If we run this program now, we get the answer 45. So that's good. Our program runs correctly. Just as a little aside, what happens now if we change the angles from X and Y from 10 and 10 to 11 and 10? So the ball's no longer located 10 meters away from us horizontally, it's located 11 meters away from us horizontally. If we run that code now, we get a different answer. The ball's located further away, and so than it is vertically. So we'd expect the angle to be less than 45 degrees. And here you see the answer displayed on the screen. It's 42.27 and so on. Quite a large number of digits displayed there. As a general rule, the number that you see displayed and highlighted there in blue, 42.273689 and so on, that's got far many more digits displayed than would be of engineering relevance. So it would be handy to be able to display that number to a more restricted number of digits. And I'll show you later in today's lecture how to control the display so that it doesn't display the 10 or 12 digits there. Notice what I also did. So there's no way of me of externally verifying without writing a different program or through some other independent means. I don't know whether the answer 42.273 is correct. It does satisfy one sanity check though. We know the angle should be less than 45 degrees because the ball is now 11 meters away from us and only 10 meters high. So as the ball gets further away than it is high, we would expect the angle to drop below 45 degrees. So that's another good, for engineers to be able to, when they're writing computer code or indeed using someone else's computer code, it's a good idea to have some idea of does the answer make sense? I don't know if the answer 42.27 is correct, but I know it satisfies a basic sanity check in that it's below 45 degrees because of the reasons I explained before about the relative distances. If I now run, I'm going to run this code a third time, a variation on this code a third time. What you see here now on the screen is the same code, except we're using prefixes for math, ATAN, and math.py. So if you run this code now, we would also expect it to produce. Apologies, wrong one. Let me run that again. Excuse me. There we go. So we know the answer is correct, 45 degrees, as I said before, but this time we're using prefixes. So we've got a couple of ways. We've got the wrong way. we've got the import without prefix, and we've got the import with prefix. So that's really good to know. Let me just break out of the presentation mode, and I'll drop back to the Wonderful. So that was our live demo of the program with a library function. I'm going to look more generally now about importing from other places. I'm going to use the terms modules and packages as interchangeable for today's lecture. That's not strictly correct. We need to see more of the Python language in use before I can usefully clarify for you from the differences between what a module is and a package. If you want something to think about for now, you can think of a module as being a special case of a package. The package is the more general terminology. I don't care about the distinction for today's lecture. But what I do care about is that we're importing code and sometimes data from places outside. And I'll call those outside places libraries. So importing what's needed is a sensible idea. It's also important to, it's a good idea to only import only what's needed. One of the problems with the earlier version of the import statement that we saw there before is that by importing access to the math library, we might actually accidentally get access to a whole lot of other functions that we don't want. And I'll show you a problem with that in just a few slides. So I want to clarify, I want to just elaborate and emphasize this difference about importing for use without a prefix and importing for use with a prefix. As a general rule, I would suggest in this course and in general and beyond it, that the importing for use with prefix is the standard and preferred way to import. It's the way that avoids unintended consequences that I'll demonstrate for you in a few slides. So importing for use without a prefix, the code that you see before you there on page 12, you've seen before. It's code that we just ran in PyCharm, and it's a cut and paste from code that we saw earlier today. The key point that I want to draw your eye to is that we're from math library, we're importing the arctan function and the pi constant. Now, the good part about importing for use, importing from libraries without the prefix, is that the Python code's easier to read. What do I mean by that? I mean, it's easier to read because we haven't got this math dot prefix floating around. It's a little bit, it's a notational overhead that we've got to carry around these prefixes all the time in order to unless we use if we import with prefixes, by definition, we need to use those prefixes. And that means our code gets a bit more cluttered. From a pure algorithmic perspective, from a mathematical perspective, if you like, or a simplicity perspective, that would be even better. The code that you see on the screen before you is easier to read, easier for humans to read. It's no more or less difficult for the Python interpreter, but for humans, it's easier to read. And for that reason, I've given it a green tick. Unfortunately, it allows what's known as name conflicts. And I'll elaborate exactly what I mean by that in a couple of slides. But because it's got a red cross next to it, a name conflict is not a good thing. Sort of gives it away in the name. Conflict is generally something to be avoided. And certainly we don't want name conflicts in our Python code. Here's what I mean about name conflicts. If we're importing from external libraries, unless we're careful, we might find that we import from two different libraries, and each of those contain a function with the same name. Can you see the problem? If we make access to two or more libraries at the same time, unless if we use this variation of importing for use without a prefix, we run the very real risk of Python being unclear of which function was intended. Two libraries each containing a function with the same name, and yet the Python interpreter doesn't know which one we're using. So I'm going to give you an example. The best example I can come up with makes use of a language feature that's really important, but that we haven't quite seen yet. We're going to see it later today. So what I want to do is draw your attention to the bottom of this slide where I've got a green tick and a red cross. We've made use of this function exp. This is the the exponential function that you might remember from high school mathematics. Then I've got a square bracket. The square bracket's going to be something called an array. We haven't seen arrays yet. We're going to see them later in today's lecture and use them extensively, but I haven't seen them. We haven't seen them before now. So just to make you aware of that. But here's the thing. Just accept that at the moment we have these things called arrays. What's important here is that the what you see on the screen in the dark square, the dark rectangle, is done at the console, and I'm attempting to evaluate this function exp from two different places. One is from the math library, which we've already seen, and the second one is from something called NumPy or NumPy. It's another library. So we've got two libraries, math and NumPy or NumPy. I don't know which one I'm going to call it. Let's call it NumPy for now. We've got two libraries. Inside those two distinct libraries, we've got a function exp. If you zoom in and look at the first three lines from the console, the first line says from NumPy import exp. That's great. That says we're going to use the exp function from library NumPy. The second line on the console says that I've got it's the code that you see at the bottom of the slide with the green tick. X is equal to exp012. If you're wondering what that means, I'm going to calculate the exponential function of the numbers 0, 1, and 2 in one line of code. Rather than doing it one after the other, I'm going to do it in one line of code. That's all it does. Details don't matter, but the point is the third line of code in the console is, so the second line evaluates X, third line prints X, and here you can see three numbers in square brackets. The interpretation doesn't matter for now. I'll give you a demonstration live in a few minutes. What the point is that if we import the exp function from the NumPy library, all is good. X equals exp012 works, no problems. Tick. Let's now try importing the exp function from the math library. Remember I said the exp function appears in both the NumPy library and the math library. Now let's import it from the math library. X equals exp012, same line that we executed before, but this time Python says can't help you. Can't help you. What's going on? Well, the error says must be a real number, not a list. The problem is that even though the exp function exists in both the NumPy and the math libraries, the implementation's different. And that's why we've run into problems here. The exp function in the math library expects not a list of numbers or an array of numbers. It wants a single number, just like you saw at high school. You type in a number and you calculate the natural exponential of it on your calculator. That's the way that the math version of the exponential function works. The NumPy library is more powerful. It can calculate not for just one number, but a list of numbers. So that is a real problem when we're writing Python code and we're bringing in functionality from outside places, because there's no guarantee that we're not going to bring code in from multiple libraries. We don't expect the authors of those libraries to have communicated and avoided a name conflict. That's not their problem to solve, it's our problem. And we do that with prefixes. So here's a second piece of code. Again, what you see on the screen here now, you've seen before. We've run it in Python, in PyCharm a few minutes ago. This is the same code that we ran before. It's for use with prefixes. So you can see now that I've importing from the math library. That says to Python, get ready. We're going to use function. We're going to make access. We're going to exploit access to the math library. When we want to use a function, for example, atan from the math library, we have to write it as math.atan. When we want to use a constant that's available from the math library, namely math.py, we have to write it out. So the disadvantage indicated with one cross is that the Python code's a little harder for humans to read. It's a little harder because we've got to carry around these prefixes with us as we go. But that slight disadvantage is more than overcome because we eliminate name conflicts. Because we're explicitly saying, I want to use the atan function that's in the math library. I want to use the pi constant that's in the math library. And for that reason, for avoiding conflicts, for name conflicts, import with a prefix is the standard, and I would say for this course, the preferred method of importing. There's almost no disadvantage to using prefixes apart from this fact that the names get a little bit longer. So here's some code. We haven't seen it before, but remember I said before I showed you on 2 slides ago, the problem with the exp function was that it appeared in both NumPy and math. Okay, page 15. Here we now have a piece of code. We're going to import from NumPy and import from math. So the top 2 lines of the code there, all they do is tell the Python interpreter, get ready, we're going to make use of these libraries. Doesn't say which functions we're going to make use of, doesn't say which constants we're going to make use of. All it says is we're going to use in our code, or we're probably going to use, we're planning to use both those external libraries. And so now when we write in the 3rd line of code here, x equals numpy.exp, we're being absolutely precise. We're telling the Python interpreter, use the exp function, but use it from the NumPy library. Don't use any other one. In particular, don't use the one from math. Just use the one from the NumPy library. And then we can print the value. We then might want to use a different function that's available in the math library, cos, the cosine function. You've seen that at high school. You probably haven't seen the Python code at high school, but you're making use of the cosine function. Inside the math library is a cosine function. And so we're able to call that math library cosine function by using the prefix math dot. So what you see here on the slide before you is the first example in this course of where we're making use of 2 external libraries at the same time, one called NumPy, one called math. We're using one function from NumPy, we're using one function from math. And there's no problem with that code. That's well-written code, unambiguous, and it'll run correctly. And the reason it runs correctly is that we're using prefixes to make clear which exponential function we're going to use. If we didn't use that prefix, by the time we got to the 3rd line of the code, Python wouldn't be clear about which function to use. Actually, it would be clear. I think the way it would go, it would use the most recently defined version of the function. The most recently defined version was defined in the 2nd line of the code. So I think that code would throw an error because it would, at the 3rd line, try and use the exponential function from the math library instead of NumPy. So that's a beautiful little piece of code that allows us to be absolutely clear about which library function to use. It's also possible. Remember I said before, it's a little bit clumsy sometimes to be able to import from an external library and have to carry around the prefix. The names of the NumPy libraries as NumPy and math, they're fairly short strings. Okay, NumPy's got 5 characters, math has got 4. It's not too inconvenient to have to carry around these prefixes NumPy and math dot. We can do a little bit better though. We can import a library and then in the same line introduce a nickname or a local name for that library. So, and that comes from using the Python keyword as. So the way that that's used is in the first line here, import NumPy as NP does 2 things. First thing it does is says to our Python program, we're gearing up to use the NumPy library. The second thing it does is to say, I don't want to use the numpy string. It's a bit long. Use NP instead. So when it comes to using prefixes, the third line of code, x equals np.exp, that means using the numpy version of exp. It's just that we can use the text string np as a nickname, a shorthand. And it's no exaggeration to say that most code that you write in this program is probably going to have its first line as import numpy as np. It's almost like just a way of getting started in your code. Import numpy as np, that means great, you're ready to use the numpy library if you need it. And you're going to use the shorthand np. And likewise, import math as m means use the math library, but instead of having to type math.function, you just type m.function. And there you can see it on the second last line of this code. Y equals m.cos0 means calculate the cosine function with argument 0. In doing that, use the math library, but use the shorthand. So this is when I said that we're going to use the prefixes as the preferred method of import in this course. It's import with prefixes, but then with a name change. We're almost always going to use abbreviated forms of these library names as local nicknames. Makes the code, it's almost like you get the benefit of both worlds. You get short code, which is easy for humans to read, but you get the benefit of avoiding name conflicts by using the prefixes. As I said, there are many libraries in Python, and the list keeps growing because Python's a very popular programming language. We're going to use a number of them in this course. Here are 3 of them that we'll make substantial use of. I would even argue that it's NumPy and Matplotlib. I've indicated 3 here: Math, NumPy, and Matplotlib. In order, the math library contains basic math operations and constants, exactly like we've seen already in the code. Trigonometric functions, exponential functions, constants like pi and e, those sort of things are all part of the math library. If you're familiar with the C programming language, the math library in Python pretty much consists of the functions and constants that are in the C programming language. They're important, but they're also quite restricted. And in particular, they all rely on calculating functions on single numbers at a time, not lists or rectangular grids of numbers. NumPy, which is short for numerical Python, is a large collection of powerful mathematical functions for scientific computing. What does that mean for us? It means the ability to do things with large data sets. We haven't seen them yet. We'll hopefully see some later in the course. But it also uses it's also able to perform mathematical operations, scientific operations, on not one number at a time, but collections of numbers. And we'll call those collections of numbers, arrays or matrices. You can think of a rectangular grid of numbers. We've already seen a version of this when we demonstrated the exponential function. Remember, it operated on the 0, the 1, and the 2 all together, and it combined in a list. That's the sort of thing that NumPy does. It allows you to operate not just on one number at a time, but whole collections of numbers, and not just 3 at a time. I'm talking 3 million at a time, 30 million at a time. Huge data sets and very sophisticated operations on those large data sets. And that means for engineers, that is gold. That means that if we're solving engineering problems, it's almost never is the case that we have to go back to fundamental principles and write our scientific computing programs from scratch. It's almost always the case that someone else has written some code that we can make use of and employ for solving our engineering problems. And NumPy is the gold standard for mathematical functions for scientific computing, engineering computing, large data sets, matrices and arrays, and a whole lot more. We'll use it extensively in this course. And the third one, we haven't had call to use it yet, but we will in today's lecture. It's for visualization. So if we want to create plots of curves, we're going to produce some plots of lines today. If you want to produce plots of curves, animations, interactive visualizations, there's a library called matplotlib, and I'll show you some of the functions in it in just a few minutes. But matplotlib is a visualization library, and the syntax for the visualization closely follows the MATLAB programming language. So you'll see on this one slide here that up until this year, ENGG1003 was taught with a mixture of MATLAB and C, and we're really getting the benefits of both. What C was pretty good at is mathematical functions through the math library, but often you've got to build a lot on the basic math library. What MATLAB's good at is visualization, is taking numerical results and presenting them as curves or surfaces or other visual displays. Actually, Python's a lot better at it. There's a lot more functions in Python, but we're really getting the best of both worlds with Python. We've got the numerical operations and a lot of the programming efficiency that comes from C, but we've got the ability to use visualization that comes from MATLAB. And you'll see the library here name is a bit of a cheeky reference to MATLAB. It's called matplotlib. It's a bit of a mouthful when you've spent a number of years programming in MATLAB, as I have. But it's really saying most of the syntax for matplotlib comes from MATLAB, but within the Python programming language. Okay, time for a live demo of importing. Let me break out of my screen here and go back to PyCharm. Presentation mode. So this program, we've seen it before. We've run it before. It's the program works. It's back to the ball angle calculation problem, but it's importing from the math library, importing the function atan and the constant pi, but it's doing it without prefixes. So when we run it, it runs correctly. We saw that before. So this is the first example of where I'm showing you code that works. It works correctly. It just it's the first example of code that works, but I would recommend against using this method. And I've said it a couple of times now that my preference, my advice to you is that you use the prefixes. So this is code that works. It's just waiting for a bug to happen. If we were to expand on this code and start building more functions into it, we would run the real risk that as we added access to more and more libraries, we'd run across this function. If we ever use the exp function, it occurred in the math library. It works, but I would prefer that you didn't run it. Let's have a look here. If I go to the console, just bear with me for a moment. Okay, so now what I'm going to do, run for you live the example that we saw on page 13. So I'm going to, from the NumPy library, I'm going to import, sorry, my mistake. X is not defined in the NumPy library, but the exp function is. So you see that it appears that nothing's happened. From NumPy import exp. All it does is gear Python up to be able to use the exp function when we need it. So now we can say x equals exp 0, 1, 2. and then we print X, and we print 3 numbers there. So the interpretation of those numbers is that we're calculating the exponential of 0, the exponential of 1, and the exponential of 2 in one line of code up at line 4. So you can see the numbers 1, 2.7, 7.3. They're the numbers that occur in this list or this array here. In fact, when I say X equals exp in code, what I would actually do, I would prefer to use this with a prefix. Oh. No, I can't do that yet. I'm being clear. Sorry, back that up. When I do this, I'm telling NumPy every time I use exp, I'm using the NumPy version of exp. This was to illustrate name conflicts, not this example was to illustrate the problem, not the solution. So let me back that up. Okay, so let me from the start, we import exp, we calculate x, we print x, and all's good. Okay. Let's now import from math, import exp. And again, no problem doing that. We've told Python that every time we use the exp function, we're going to use the math version of it. We don't have to redefine x, but there it is. That's the problem. We tried to compute the exponential of x, and it tells us there's a problem. It's the same line of code that worked in line 15 that's a problem, that worked correctly in line 12. The difference is which external library are we drawing the exponential function from. So that was the problem there. That's the illustration of name conflicts that we avoid by using prefixes in our code. So now if I go back to excuse me. Bear with me. This code here is we're importing with prefixes. So we're importing from the NumPy library. Just remove those 2 lines there. So we're importing from NumPy, importing from math. The code that you see there in lines 1 and 2, all it does is tell Python that we're gearing up to use those libraries. If we run that code now, all is good. The first line of calculation is in line 4, where let me highlight it for you. The first line of code is where we use the NumPy's version of the exponential function. And then sure enough, when the code runs, we get the 3 numbers computed simultaneously. In line 7, we're using the math library version of the cosine function. You might remember from high school maths, cosine of 0 is 1. So if we use the math library version of the cosine function, we can compute the cosine of 0, which is 1. And sure enough, we see the answer 1 in the output. So this is really interesting code that we see here on the screen here. We're drawing from 2 external libraries where we know there's the potential for a name conflict. We know that because from experience earlier today, the exp function appears in both the NumPy library and the math library. And yet we're avoiding a problem with name conflicts by using these prefixes here. So that's a really powerful illustration of how the use of prefixes can avoid actual problems with name conflicts. So there's still a potential problem, but we avoid it by using the prefixes. So where are we up to? imported with prefixes. We avoid the problems. I introduce the names of the libraries. And there'll be a few more that we use, and we'll make those clear. But for the moment, Math, NumPy, and Matplotlib are the three that we use. And I would go so far as to say that it's mainly going to be NumPy and Matplotlib. Math is pretty much a subset, a very small subset of what's in NumPy. And we've just given a live demonstration of importing. Good. Okay. I said there were three things we're going to do today. We've already covered off the first two in the first hour. Essentially, in the first hour today, we've covered importing from external libraries. Now we're going to introduce plotting and a couple of other features. We're going to start off with the plotting, and through the plotting process, we'll see the other features that I want to introduce. We saw the mathematical expression that you see on the screen here in last week's lecture. It was the vertical position of a ball at time t. This was the very first example that we ran in our very first program last week. I might not have given the expression as a nicely typeset equation on the screen like this, but this was the expression that we evaluated in our Python code. It's the expression of the vertical height of a ball at time t. And so we're going to represent the vertical position of y of the ball as the variable y. And we're going to calculate it at time t. And the interpretation of the various terms in the right-hand side of this expression are v0 is the initial upwards velocity, and g is the acceleration due to gravity. And I've indicated the units here on the dot points. What I should also say is if we use those units, these are the metric units, then the vertical position of the ball is indicated in meters. And so if we're given the initial velocity and the time, we can calculate the height of the ball. The sort of the mental model that you should have in mind is that suppose we've got a ball or some sort of projectile, maybe a rocket at ground level, and it's launched from the ground so that at time 0, it has an upwards velocity of v0. So there's some launch mechanism. We either kick the ball with our foot or we've got some sort of rocket propulsion system that kicks in and gives an impulse to the ball or the projectile at time t is equal to 0. And the expression that you see on the screen there calculates the vertical position of the ball at time t. Okay, so far we've seen all the key elements of that expression in last week's lecture. Now we want to extend that code or that problem setting so that to calculate the height, not just any specific time t, but every millisecond for the first second of flight. So that's the first challenge for us to solve today. We're going to do some calculation of not just one number, but a collection of numbers. And we want to take the output and plot it graphically so that we can visualize what the ball does or the projectile does. Let me call it a ball. We want to visualize the path of the ball with time. And we haven't yet seen how to do that. So there are two challenges for us on the slide here. The first is to calculate with a set of numbers rather than just one number at a time. And the second one is to plot the outputs graphically so we visualize. Here's our code to do that. And again, I will run it for you in our little breakout live demo in a few minutes' time. Our code starts off straightforward enough. We input NumPy as NP. Remember I said that was sort of the code that we used to get started, because there's almost nothing wrong with importing from NumPy because it opens up a huge number of functions and code for us. Second line is we're going to make use of the Matplotlib package. And there's one small feature there, if you're following carefully, that we're importing matplotlib.pyplot as plot. Our lab exercises this week step you through that in a little more detail. what I want you to take home from what you see on the screen here at the moment, the second line of the code allows us to import from the matplotlib package, and we're going to make use of that through the prefix plt for plot. The next 3 lines of code, the first 2 you've seen before. We give the value 5 to the variable v0, we give the value 9.81 to the variable g. They map directly to the expression that you see on the slide there on page 19. So far, so good. What about this next line? T equals np.linspace 01001. We need to unpack that. I just want to draw your attention to it here, and we're going to unpack it in the next couple of slides. So we've defined this quantity T. It's actually going to be not a number, but a collection of numbers. The next line of the code, y equals v0 times t minus blah, blah, blah. This bit here, y equals. That is a direct mapping of the expression, the mathematical expression that you see on page 19. It's a direct copy. Y equals v0t minus a half g t squared. Remember the use of the double asterisk is Python's way of representing to the power of. So t star star 2 is t squared. And then we've got some plots instructions at the bottom. So there's our code, top to bottom. It'll run, and I'll run it for you in a live demo in a few moments. But before I do that, there's a couple of things I want to illustrate for you. One is what the output looks like. When we run that program in PyCharm, I'll do it live for you in a few minutes. This is what you see. This is our first plot that we've seen in Python. Now, a number of you, based on your experience in the week 1 lab, actually got to plotting some results at the end of week 1. That's great. You actually pushed ahead into week 2 content, and I've got no problem with you doing that. But for the class, for those of you that didn't, this is probably the first time you've ever seen a graph output from Python. So you see a couple of things here. One is that you can see that the graph starts down towards the bottom left-hand corner at the point 0, 0. Remember, this is the trajectory of the ball, the height, not the trajectory, rather it's the height. So that the ball, when started with an initial velocity of 5 meters per second, under the influence of gravity, it gets higher and higher until it reaches a peak height of about 1.2 meters after about half a second. And then the ball starts to drop, so that by the time we get to 1 second, the ball's almost back down at the ground again. So the ball only gets about 1.2 meters above the ground, and it's in the air for a bit more than a second. Why do I know it's in the air for a bit more than a second? Because after 1 second, the height's almost back to 0, but not quite. But the plot's also got some additional features. It's got some units indicated here on the horizontal axis. It's got some units indicated here on the vertical axis. There's a blue line, and it's all produced with that code. That's what the output will look like. Let's step back. There's 2 key lines of code that I really want to explain to you that are this first line that you see here on page 22. It's one line from the code on page 20. T equals np.linspace 01001. Let's unpack what that means. Remember the np prefix? That's because we've told Python we're going to import the numpy library and refer to it as np. So what the first part of that code does is we know that it's going to make use of something inside the numpy library. It's making use of something called linspace. Linspace is short for linear space. It's taking the interval 0 and 1, indicated here by the first 2 parameters that we pass in, or arguments that we pass into the linspace function, and then we put and the number 1001 means that we want to create 1001 coordinates on that interval. Where does the number 1001 come from? It comes from the fact, remember the problem specification was that we wanted to calculate the height at every millisecond. We need to space the values in the t variable, the t array. We need to space them by 1 millisecond. So in fact, what we want to do is create 1001 coordinates, because we need to include the endpoints 0 and 1, and we want to space them by 1 millisecond, namely a time of 0.001 seconds. So this line of code, one line, uses the NumPy library to create 1001 values stored in an array. Now, we're going to have a lot more to say about arrays in the weeks ahead, but for now, just think of the array T as a collection of boxes in computer memory. I don't care about how they're actually stored. I don't want you to even worry about that at the moment. But I do want you to have a mental model for what it looks like in terms of Python code. And it looks like to store values in an array called T means that we store numbers in boxes, computer memory locations, consecutively from 0 upwards. So the first element of the array is T, left square bracket, 0, right square bracket. The square brackets are a way of indicating a label associated with each box. The 0 indicates the address of that box, and the expression T0 is the value that's stored in that box, and so on up to T1000. So we've created our first array. We're going to have a lot more to say about them in the weeks ahead, but here's our first example. Really powerful, because it means we can compute not with just one number at a time, but thousands of numbers at a time. So what you see on the slide here is, again, an extract of the code that came from a few slides previously. Y equals V0t minus a half GT squared, written in Python code. Looks like an expression that we saw last week. It is an expression that we saw last week, but there's a really big difference. The difference comes from the fact that T on the right-hand side, you can see it appears twice here. The T is not just a number, but it's an array, a collection of numbers. This expression is really powerful. It says y should be computed as an expression that you see at the top of the slide, but done for not just one value of T, but for all values of T, or all values of T in the array. So not just for T0, but for T0, for T1, T2, up to T1000. And remember, the values stored in T are the times 0, 1 millisecond, 2 milliseconds, 3 milliseconds, up to 1 second. So this expression that you see on the slide here now is really powerful. It's powerful because it looks like an expression that you've seen before, and is an expression you've seen before. But because T is an array, Python automatically says, I know what you mean. You want me to compute the value y, namely the ball height, not just for one value of time, but for all the values of time that are defined in the array T. That is really powerful, because it says we don't have to worry about telling Python, we've got 1001 time points, here they are, compute this expression for each of those time points separately. One elegant line of code, one powerful line of code, introduces the variable y, which in turn becomes an array of 1001 numbers, and we do it with a single line of code. So this technique of computing all numbers in one chunk is called vectorization, and Python does it particularly elegantly. Do I care as an engineer about writing elegant code? No, I care about solving problems, and I want you to care about solving problems. I want to give you methods for solving complicated engineering problems. Vectorization helps you as an engineer do exactly that. You're not worrying about writing code that steps through somehow keeping track of 1001 variables and computing expression and storing those numbers somewhere. Python does it in a single line of code. The line of code closely models the mathematical expression that it was based upon, and the tracking of all the variables happens automatically through a process known as vectorization. Really powerful. So I said I wanted to introduce plotting for you, and we've spent 15 minutes talking mostly about vectorization. That was a way of giving us something interesting to plot. The plot commands themselves are not very, they're all new. You've not seen these lines before. We've got plot, X label, and show. And they're all got the prefix PLT. Where does that come from? Where does PLT? Let's back up in the code and have a look. PLT comes because we've imported from the matplot library PyPlot, something called PyPlot package. The details this week's lab. The important part for right now is that PLT gives us the capability of plotting using the matplotlib library. So back to the code, we've got the ability to plot, and we've got the ability to put labels. Remember I said in the plot that we've got these nice labels on the axis to represent what the quantities are? We do that through these plot commands: plot, X label, Y label, and show. And in this week's lab, you'll see a whole bunch of the plotting functions that come from the matplotlib library, and they're not best illustrated in a complicated bit of code that I demonstrate for you here on the screen. Once you've got the principle that there's plot, X label, Y label, show, we'll see a couple of others today. Here's a live demonstration of simple plotting. Let's do it. Plotting something best done and shown rather than talked about. Let's bring up Python, and before I do that, I'm going to bring up the console. Okay. Oop. Sorry. Sorry, I'm trying to bring up the console. Bear with me. Console. Okay. So I'm in a moment. I'm going to show you what happened with those simple plot commands. But first, I'm going to import numpy as NP. Good. So that says to Python, we're going to make use of the numpy library. Oh, what I'm doing here, by the way, is I'm going to illustrate code that I showed you in the lecture slides as a program, but I'm going to do it at the console because I want to be able to interrogate the values of variables one at a time as we go. And that's most easily done at the console rather than in a program. But then I'll run it as a program, and you'll see the net effect of putting all those commands in a single program. So the first step was to import numpy as NP, and then I'm going to define my T expression. T equals NP linspace. So this is a function called linspace inside the numpy library. And now I'm going to define it. So the interpretation of the three arguments 0, 1, and 1001 is the first value that T takes, 0. The last value that T takes, 1. And linspace means I'm going to equally space the points 0 and 1 with 1001 different intervals, different points. And remember the 1001 rather than the 1000, because if we include the endpoints, we get one more point than there are gaps between the points. And the problem specification said that we needed to calculate the time at 1 millisecond intervals. So there's T. If I display it, it tells me that it's an array. Okay. 0, 0.001, I'm looking down here, up to 1. So it's done what we wanted to. It's created an array of 1,001 entries, and they're separated. They start at 0, they finish at 1, and they're separated by 1 millisecond, 0.001. And that's why we needed 1,001 points, because the points themselves are separated by 1 millisecond, and if we include the endpoints, we get one more than the gap, the number of gaps. Okay, if you're really following along closely, I don't want to go into details because we'll look at them in the weeks ahead. But if you look on the right-hand side, it's telling us a little bit on the right-hand window about this expression that we've created as T. Remember, I've talked about types. We've talked about integer types. We've talked about float types. We've talked about them briefly because we're going to do them in some detail on Thursday's lecture of this week. We've talked about string types. This is an array type. This is a new data type that we haven't previously seen before today's lecture. Okay, so there we've created T. This is our time index. How do we index the first value of T? We use the square brackets. And the value of T0 is 0. That's the first time instant that we're interested in the trajectory of the ball. What about the next time instant? 1 millisecond later. Second time instant, 2 milliseconds. What about the 1,000th time instant? It's 1. We started counting at 0 and we counted up to 1,000. So there's 1,001 entries. What's going to happen if I try and access a value of T that hasn't actually been defined? In this case, I'm going to try 1,001. What's going to happen? Problem. Why problem? Because we defined T to be a set of times separated by 1 millisecond, starting at 0 and going up to 1. There's no such thing as T1001. It's not been defined. And so we would expect Python to have a problem with it. And sure enough, it tells us in the error message, index 1001 is out of bounds. That says we've only got values of 0 up to 1,000, of which there are 1,001 of them. Great. But if we try and go beyond that, we should expect problems. Okay. Here's our, we better define what V0 is. V0 was equal to 5. G was equal to 9.81. And, not V is equal to 5, not Y is equal to 5. V0 is equal to 5. Good. And now we've got the expression for Y. This is this really powerful idea of vectorization, remember? So we're actually going to compute Y, not just for one value of T, but for all values of T. And we know that T is one of these things called an array. So we do that, doesn't take long. And we've computed the heights T, we computed the ball height Y. But the magic, it's not really magic, it's just the power of the Python language, is that now, if we ask what Y is, it's also an array. It's an array the size of T. It's been inherited through this calculation here. We didn't have to do anything special. We just said calculate in line 15 here on the console, calculate the ball height Y for every value of T in the array T. That's great. So we can ask what the value of Y0 is. 0 because the ball started on the ground. We can ask the height of the ball after 1 millisecond. We can ask the height of the ball after 2 milliseconds. We can ask the height of the ball after 1 second. Remember I said the ball hadn't quite reached the ground? It's a little bit higher than 0. So that's great. It's better than great. Line 15, we used the automatic vectorization power that comes from Python to compute the height of the ball for every one of 1,001 time instance separated by 1 millisecond. Trouble is, seeing that vector of numbers is not very informative. It's great to have the numbers, but we want to be able to visualize them. So in order to do that, we're going to run some code. Let me just open up the code. Okay. So here's our code. This is code that we saw in the lecture notes a few minutes ago. We imported from the NumPy library and the matplotlib library. We defined the initial velocity, the acceleration due to gravity. We defined the time instance, and I've just stepped you through on the console how that was done. We've got the line 12, which computes the ball heights. We did that on the console also. The remaining commands just plot the ball height as a function of time. Let's do it. Let's run that code. And there we see the output. So this is actually plotted the ball height as a function of time. Now you might say, that's great. Notice what are the, let's look back at the commands and notice that we've got the X labels, the Y labels. We're going to plot the first command on line 14 here, plot t comma y, says we want the horizontal axis to be t, we want the vertical axis to be y, we want the labels to be time in seconds, y in meters, and then we want to display the figure. Okay. Now you might say, let me just run that again. Let's run it again, bring up the figure. There's the figure. Now you might say, well, that looks like a smooth curve. How do you know that it's only plotted the heights at the time instance that separated by 1 millisecond? Okay, let me go back in and I'm going to introduce a little modification here to line 14. I'm going to introduce a third parameter, which is going to produce it's going to explicitly put a dot, in this case an asterisk, at each of the points in time. If we run that now, we get a curve that looks a little bit different. The line looks thicker because what's actually going on is that at each point in time, we've not got a dot, but an asterisk. But look at what happens if we zoom in now. Here you see the time instance explicitly. Zoom right in. So here we've got the time instance separated by 1 millisecond and the corresponding heights in Y. So using this variation in the plot command, if we're interested, we can actually separate each of the points that we've computed and confirm that the plot command actually does exactly what we asked it. It plotted a point Y for every point in time t, and then but only plots a little so-called line marker at those points. And the line marker here was a star because in our command on line 14 we use an asterisk. So that's great. What's actually happening with the plot command if you don't use that star is that Python says it sort of joins the dots. It literally joins the dots. It plots a point in, and then if you zoom in on this one, doesn't matter how much you zoom, you can't see the points separated explicitly because Python or the matplotlib libraries or the Python IDE is actually joining the dots. Most of the time, what you want is a smooth curve like this, but just to be clear about what it's doing, there's no magic going on. So we have now done the first, let me just bring up our We've done a live demonstration of simple plotting. So I said we're going to do 4 things today. We've done the first 3. Import from library, our first example of an import, importing in a bit more detail. We've done some simple plotting. The 4th and final thing that I want to cover with you today is to just a little bit more detail on plotting, and then illustrate how we can exert some control over numbers that are displayed on the console. So I've mentioned before, matplotlib is our friend. It's our standard plotting package in Python, and one we'll be using throughout the course. And we've also seen an array of ball heights plotted against another array points in time. And I don't need to elaborate that one. We've just run it live in the demo. So the plt dot command refers back to the fact that we've got a line in our code that imports or makes use of the matplotlib library. And that's our default plot, is to just plot a variable y in this case as a function, or as a in correspondence with the variable t. But we can do other things. We can change line colors. We can change line markers. So the plot on the left looks like one we've seen before, but there's a difference. Can you see the difference? If I was going live in a face-to-face lecture, I would pause at this point and ask you to it's a spot the difference question. How does the plot that you see on the left of page 27 differ from the plot that you see at the bottom of page 26? I'm going to give you a moment to spot the difference. They look the same, blue curve, parabola facing downwards. The difference is in the horizontal axis. The x-axis, the horizontal axis, here it's the time axis. Plot t comma y plots the expression y, the ball height, as a function of time t. If we just plot y itself, Python says no problems, I can do that, and plots it. But on the horizontal axis, it doesn't use time. It's got no knowledge of time. The plot command is just to plot the variable itself. And so the default is to plot as a function of the time index. So for us, the index is 0, 1, 2, and so on up to 1,000. So usually, while you can plot as a function of the indices, the preference would be to plot it as a function of units, because when we're solving engineering problems, it's almost always the case that the units have a physical significance. They might be a time, they might be a pressure, they might be an altitude, they might be a voltage, they might be a chemical concentration, they might be a distance in meters. They've all got a physical significance. But if you don't specify what the horizontal axis is, it just prints as a function of indices. So using a third parameter to the plot command, it's possible to change the line color. In this case, K is the Python shorthand for black line. We might want a dotted line or a dashed line. So we produce a dashed line with minus as the third parameter. That plots a dashed line in the default color. Default color is blue for Python. On the right, you see a plot command that uses red dashed lines. R for red, dash dash meaning for dashed line type. And so it's possible to come up with all sorts of interesting, extravagant, hopefully meaningful and informative uses of different line styles. We explore a few of those in this week's lab sheet, but you're also welcome to experiment and see there's different line markers, there's different line colors, there's different line styles. You can overlay markers and colors and styles depending on what your needs are in your application. We've already seen plotting points only. I already did a live demonstration for you at the console, where if you want to see the particular points that you've got data on, you can use a different line marker, in this case an asterisk, to produce a star. That's sometimes the sort of diagram that you need to see in an engineering context. Why? Because it might be really important when you're conveying an information to a client or a fellow student. It might be really important to know which of the data points you have information for and which of the ones have been obtained through interpolation or joining the dots. So in this case, uh, in a sense, this line is less informative than the solid line that we saw before. In some sense, in another sense, it's more informative because it tells us that we only know in this particular case, because if you look at the bottom of the screen here now, you'll see that time's only defined at 11 different values, not 1001. You'll see that the ball height is only defined at those particular instants of time. Maybe those measurements are coming from some instrumentation that's been connected to a chemical process, or they're coming from uh, some sort of laser distance measuring piece of equipment that only gives you distances at specific snapshots in time. In that case, probably makes sense to display the line style as using a line marker rather than asking Python to join the dots. We can go one step further, and depending on what your application is, if you're producing a graph for a report, we saw before that we're able to produce labels for the x-axis and the y-axis. So here they are. But this display here has got some further decorations. It's got something up in the right-hand corner called a legend. Legend for when we're displaying a single quantity on a graph probably doesn't make a whole lot of sense. Although in this case, it confirms for us that the blue line does indeed represent the ball height as a function of time, and it gives us the expression there. The choice of the legend here is completely up to us, and I'll show you on the next slide how to do that. So this up in the top right hand corner is called the legend. Where legends are really useful are where we've got two or more line types indicated on the same plot. Maybe you've got a red line indicating ball velocity and a blue line indicating ball height, and you want to be really clear in the plot: red line for velocity, blue for height, and you want those lines to coexist on the plot at the same time. Then a legend is really important. It allows you to use the line marker to indicate to a viewer, a reader, exactly what quantity of interest you're presenting. You can also put a title in. This is a great title, arguably not a great title, but there it is. And the other thing that you've got to look a bit closely with this plot is that we've actually exerted some control. We put a grid on. You can see this rectangular grid, and we've also got the ability to provide explicit control over the axes, rather than when we produce these plots, we just let Python decide what the limits were of the area to be displayed. If we want to control those, here's the code. So decorating a plot, again, something best done in a live demo rather than me giving you a bit this in a lecture. But here you see the code that was used to decorate, so-called decorate that plot. Plot to add a legend, plot to add a grid, plot to display a title, and code to override the default ranges. It's also possible to produce multiple curves in the same plot. As I said before, here we've got a solid curve and a blue dash curve. They represent different functions. In this case, notice how the legend is really important. The line type and the line color really allow us to easily see which quantity of interest is being displayed. And again, for engineering applications, which is what this course is all about, it's really important to be unambiguous about what information's being conveyed. One of these things might be the height of a fluid in a tank. The other one might be the concentration of acid in that tank. And you want to be really clear which quantity you're representing. So one of them might be the velocity of an unmanned vehicle, and the other one might be its altitude, autonomous vehicle, and the other one might be at altitude. So you want to be clear. And again, is it nice to produce pretty plots? Might be in some contexts. In an engineering context, it's vital to convey information in as unambiguous fashion as possible. And Python really helps us do that by producing plotting commands, providing plotting commands, which give line types, line colors, legends, and in time we'll get to exercise through the course, our ability and our need to produce curves that have got these properties. I'm not going to go through the all this code. This is the code that you see on the screen here before you. That's the code to produce the plots that you see on the slide there, the red solid and the blue dashed. The only thing I want to draw your attention to is the line at the bottom of this screen, which is the plot command in Python producing multiple curves on the same plot. And so if you look carefully, you'll see plotting t, the function f values, and the third argument is in parentheses, is in the commas, is r. That refers to a red solid line, r for red. And we've got t, g values, the second function, and then b dash dashed. That means produce a blue plot with a dashed line type. And in this week's lab sheets, you'll get to see a couple of different ways of producing writing Python code that produces multiple curves on the same plot. There's also activities in this week's lab sheet that produce not just multiple curves on the one plot, but multiple plots on the one figure. And again, that's definitely something best done with you sitting at a PyCharm IDE rather than me doing it at length here for you in a lecture. It's not to say it's not important, it's just difficult to convey the detail, and you're much better to do this sort of stuff interactively. Have an experiment, change the legend, change the title, change the line type, change the line color, and you'll get the handle of it really quickly. Before I go on to the next and final little portion of today's lecture, I do want to say, you might look at this code that you see here on the screen in front of you and say, how on earth was I meant to know about the plot.grid command? How on earth was I meant to know about plot.axis, X label, Y label? There will be occasions, and we're starting to do it already in this course, where it's easier for me to show it to you and for you to then be able to find that information online should you need it, than for me to laboriously go through every line by line. So when you're just getting started to writing computer code, often the best way to get started is to model your code on other code that's been given to you, either given to you in lecture slides or as sample solutions, or indeed embedded in the lab sheets themselves. So if you're sitting in the lecture thinking, wow, I didn't know about the plot.legend command in Python, am I expected to know that? I would say to you, wrong question to ask. In this course and in university learning, it's more about being alert to content that you might not have seen before, and then knowing how and when and who to ask for detail. And in some cases, it's as simple as jumping on Google and saying, Google, tell me about Python's matplotlib legend command. So just Google matplotlib legend Python and you'll get an answer. For this course, of course, you can always ask the question in Discord, and I'd encourage you to do it because that allows you to share your knowledge with your peers. So that's just a little note on that to make sure that you're not thinking I expect you to memorize stuff. For this course, I'm not going to expect you to memorize much at all. By practice and exposure, you'll get experience and confidence to either know you'll be able to tap into code that you've already written, or that you'll be able to find it quickly. So that's just maybe a difference in learning style to one that you've seen before. Final thing that I want to cover in just the remaining minutes is the printing variables. So plotting means we're going to produce graphs. Printing means we're going to print to the screen. Now, we've already seen some issues about printing. I think one of the very first commands I showed you last week was, if we want to know the value of a variable, we can just print it either at the console or in a Python program. We can print variables. We can print string variables, so we can print numbers, and we can print strings. And the command at the bottom of the slide there shows you how to print a string. That's good, but we can do a lot better. And again, as we're looking increasingly at producing reports or reporting that's of engineering relevance, We want to reduce all sorts of ambiguity. So we want our print displays to be informative, but we also want them to hide information that's irrelevant. And so what I'm going to show you in the last few slides of today's lecture is how to do both those things. How to produce information that is unambiguous, so it captures the intended meaning correctly, but also doesn't produce additional information that's not helpful. And what I'm talking about there is producing numbers that have got 10 or 12 decimal places. That's not relevant in an engineering context. Let me show you how to get around that problem. Suppose we've got a variable v1 and it's got the value 10. It's actually going to be a real number, a floating point, a float number, and I indicate that with the point 0. So this is a floating point number that's expressible with a finite number of decimals, in this case 10.0. Suppose we want to produce the output that you see on the screen in the grey box. V1 is 10.0. So that makes it unambiguous that it's the variable V1 we're displaying, and that we're displaying it to, in this case, 1 decimal place. There's a number of ways of displaying these variables, and I've seen people experimenting in the labs and in the Discord channels about how to display values. I don't necessarily have a preferred or recommended way, but this is the way that I would primarily use. If we want to display the variable v1 is 10, literally like that on the screen, we would use a print statement, which has got two components. The first one is a string indicated in the sort of the bluey grey text, and the second one is a format statement, which is going to convert the number v1 to a string. The key thing I want to draw your eye to on this screen is the use of these curly brackets. They're being used as a placeholder in the string. They say where we're going to place the value that's going to subsequently be produced. So we want the string to say v1 is in that place a number. We're going to use the curly parentheses to indicate that as a placeholder. And the format command converts the variable v1 to a string. So that's good. We can produce one, and I'm going to do this live for you in just a moment. And we can produce one variable and text together in one line. We can produce several variables using the same idea. This case, we need not just one placeholder, but two. Notice down the bottom, we've got v1 is placeholder, comma, v2 is placeholder, and then a format statement, which tells us to print the values of v1 and v2, those variables. And in this case, the two curly brackets tell us that we've got two numbers to display and they're placeholders. And the format statement says we're going to display two numbers, not just one. And then they need to be produced in the order v1 and then v2. And the ordering here is important. This v1 matches to the first gap, the first placeholder. And this v2 on the right here fills in the gap in the second set of placeholder curly brackets. Okay, 2 slides to go. Controlled printing, we want to be able to display decimal numbers. We want to be able to use so-called scientific notation or exponential notation, and we want to be able to display strings. Strings so far are going to be pretty easy, so that what I want to draw your attention to is the display of the real numbers and the integers. Suppose you want to display as follows. Suppose we've got a real number that takes as value 12.89643, an integer 42, and then a string which consists of the characters some message. Suppose we want to write a program that displays in the grey box here that information in two different ways. The first one says real is equal to 12.896, comma, integer is equal to 42, comma, string equals some message. And the second version is a variation on that. So what you see at the bottom of the screen here is the Python code to be able to do that. We define our real variable, our integer, and our string, first 3 lines. And then we've got two print statements that show how to format that information. Now, you will see those print statements, they're starting to look pretty complicated. There's a lot of detail packed into them. Let's unpack them one at a time. Controlled printing, the first call to print, we see remember before we had these placeholders that were just empty? Now we're actually going to put things inside the placeholders. And the stuff we're going to put inside the placeholders is our way of conveying to Python the format that we want to use to display those numbers. So don't worry about memorizing anything on this screen. What the take-home message is that you've seen it, you can refer back to it, and in this week's lab activity, you'll know the rationale for what's going on. The key message here is that inside the placeholders is important information about how we want the number to be displayed. And so the inside the first placeholder is :.3f. That's our way of conveying to Python that we want to display the floating point number, hence f. Remember, think of it as a real number, as compactly as possible using 3 decimal places, using 3 decimals, and that's what the 3 is about. So if we run that, what we see is the number displayed as 12.896. The 896 are the 3 decimals that we want to display, and it chops off or rounds the information that follows in the real number after that point. :D represents an integer as compactly as possible, and :S we just write the string. One final example, and it really starts to look fiddly, but it's a great activity to sit at the Python console and experiment with, is the first placeholder is :9.3e. The E indicates that we want to represent the number in exponential or scientific format, and the 9.3 indicates that we want to represent the number in a field of width 9 characters using 3 decimals. So if we run that, we see the number displayed as 1.290, 3 decimals, 290, using a width of no more than 9 characters. And likewise, we can write our integer in a specified field width. And I really don't want to go into any more detail at this point because it's best demonstrated. I'll give you a really quick demonstration here live. We'll wrap the lecture up, and then what I want you to do in this week's lab is work through those examples where you get to experiment. It's not about memorizing, it's about familiarization. And then when you need to express those numbers in a pre-specified format, you've seen it before and you can go back and do it. So let's do a super quick live demo to finish off the lecture. Let's have a look here. Let me just go to console. Okay, and I'll get this right. Console. Okay, our first expression was v1 is equal to 10.0. There it is. If we look carefully on the right hand side, we'll see v1 is equal to float 10. That means it's a floating point number, a real number with value 10. And then we want to display our message v1 is placeholder dot format v1. And then we get v1 is equal to 10. So if we were to change v1 to a different number, up arrow through our console, display it, there we get it, which is great. That means we can produce a number and we can display it on the same line as some text, rather than producing a number in a report and having someone think, is that variable v1 or v2? Is that the altitude of the autonomous vehicle, or is it the depth of the submarine? We're being clear about what we're displaying. Let's now introduce our second variable. v1 is equal to 20, and we can, here's one I prepared earlier. v1 is equal to placeholder, v2 is equal to placeholder, and then we display them. Done, just like in the lectures. If we now introduce the variable, what was the name of the variable? What was it called? It's called R. R is equal to 12.89643. D was equal to D. What was it? What was the integer variable called? I. I is equal to 42, and S is equal to some message. Now we've defined floating point variable R, integer variable 42, string variable some message. Then we can print them. Here's the first variation that I showed you in the lecture slides where we're producing real numbers to, let me just focus on the real number for a moment. Sorry, what I'm trying to do is make the display as clean as possible. Okay, so let's let's experiment now with changing. Why is it doing that? Just drop back to this one, that'll do. Okay, so there's our number. And now if we use the second type of formatting, the more complicated format, this is the second one. Oh. No, never mind. Best done. We're hard pressed on time, so let me pause at that point. What it shows you is that this sort of stuff is best done sitting in a computer lab, hands-on, rather than trying to do it in lecture mode. So let me just break out of that. We'll break at that point, and that's the end of our lecture content, and we're pressed right up hard against time. So thanks so much for your attention. We covered some really important stuff today. We also moved through at a reasonably rapid pace. That's why you've got an opportunity of a week to absorb it all and attend this week's lab, where you'll get your hands on with quite a few activities, from importing from external libraries, plotting, and some exercises in formatting numbers. Hope you've got a bit out of today's lecture. I look forward to catching up with you on Discord and at some of this week's face-to-face and Zoom labs. Remember, only the face-to-face labs are the mandatory attendance. The Zoom labs, we don't record attendance, but you're encouraged to attend. Thanks so much for joining me today. I'll be on Discord shortly to answer questions along with Brenton. Until we catch up next, I'll say bye for now. Thank you.